Hello everyone. Today I am going to explain to you all about binary search algorithm. Binary search algorithm is a searching algorithm which works basically only on sorted input array. So, basically, if you are given an input array which contains integers only, and you need to find some integer which is present or not in this input array, like suppose in this input array you are told to find whether 12 is present or not, and if 12 is present, then also return the index at which this 12 is present in the input array. Then for this sort of problems, binary search algorithm is useful. But as I said, binary search algorithm can be applied only on sorted array, because the algorithm is that only. Basically, it requires the array to be sorted. So if the array is sorted only initially, then you can easily apply binary search algorithm on this array for finding the target element. So let's see the binary search algorithm in action. So for doing the binary search algorithm, what we do first, we initialize a left pointer, which let's denote it by L, and a right pointer, let's denote it by R. So we initialize two pointers, left pointer and right pointer. Left pointer is always initialized to the first element in the input array, L. Okay, and R pointer is initialized to the last element. Okay, so let's try and run the binary search algorithm on this input array for and try to find whether 12 is present or not, and if 12 is present, then return the index of this 12. So for what we do first is we calculate the mid pointer. So for formula for the mid pointer is left plus right pointer divide by 2, and this division is a integer division. Integer division basically is a floor operation. Okay, so L is 0 index, and R is 13 index. So 0 plus 13 by 2 integer division would give us 6. Okay, so basically our M pointer would become here at the sixth index. Okay, then basically uh, we check whether the value at this middle pointer, which is 15, is it equal to our target element or not. So 15 is not equal to 12, which is our target element. So then we see that 15 is greater than our target element. So as we know that input array is sorted, so we can safely assume that since our middle element is greater than the target element, so target element would definitely be present on the left side of this middle element. So what we do, we basically ignore this right part of the input array, because we know our target element would not be present here since the input array is sorted. So let's ignore this part of the array. Okay, and for ignoring that, what we do basically, we update the right pointer to be mid plus 1, and we can also ignore the mid pointer as well, because we know that mid value, which is 15, is that is also not equal to our target element. So we ignore the part of the array including the mid pointer, and right pointer would be updated to mid pointer plus 1. So right pointer would come here, and okay, so we will ignore this mid pointer as well. Okay, so this is what the new condition looks like. This is the left pointer, and this is the right pointer, and this is the array which has been reduced to half now under consideration. And okay, so now we repeat the same thing again and again till we find the target element. So again, the middle pointer, which is left plus right by 2, which would come out to be 0 plus 5 by 2, that is 2. So middle pointer comes out to be here, which is the index at element at index 2, and we see that element at index 2 is 5, which is lesser than 12. So basically, in the sorted array, we can safely assume that since middle element is lesser than 12, so 12 would definitely be present on the right side of this middle element. So again, we can ignore these left part of the input array, including the middle pointer. And for that, what we do, we update the left pointer to be mid plus 1. And sorry, actually, initially during updation of right pointer, I told that we do update the right pointer to be mid plus 1. Actually, it is not mid plus 1. We update the right pointer to mid minus 1. And during updation of left pointer, we update the left pointer to mid plus 1. Okay. So left pointer would come here, and basically then we can ignore these part of array. Okay. So this is our new situation. Again, we repeat that same thing. We will repeat this same thing till we find the target element, which is 12, or till the time comes when left pointer actually moves ahead of the right pointer. If left pointer moves ahead of the right pointer, then we say this is invalid case, so we end our operation, binary search algorithm, and we can say that the element 12, which is our target, is not present in this array. So let's calculate the middle pointer again. 3 plus 5 by 2, which is 4. So middle pointer would come here. And as we can see, this time the middle pointer is pointing to 9, which is again lesser than 12. So we again say that we need to move on the right side. So we again update the left pointer to be mid plus 1. So left pointer would come and would coincide with the right pointer. So right and left both are pointing to the fifth index. And as done earlier, we ignore this left part of the array. Okay. Now, still right pointer and left pointer are coinciding, but still left pointer, like if I write like this, left and right are coinciding, but still left pointer is not crossed. Left pointer has not crossed the right pointer. So we can say that still this situation is also valid. So we again calculate mid pointer, which is left plus right by 2, which is 5 plus 5 by 2, which would come out to be 5 only. So basically our mid pointer would also come here only. So everything left, mid and right are pointing to one element only. And we see that this element is now finally our target. So we have found, using binary search algorithm, we have found the target element, which is 12 in the input array. And we have also found that this element target was found at index 5. Okay, so this was the binary search algorithm in action. Now let's see the pseudocode of this binary search algorithm. So this is the pseudocode. Basically, you can assume that you would be required to create a binary search algorithm function, and that function would be given an input array on which you need to find the target element. Okay, so input array and target. And here I have written the left pointer as the start pointer and the right pointer as the end pointer. So you can assume start st means left pointer and end means right pointer. So we initialize the start pointer to 0 and the end pointer to n minus 1, which is the last index, and here is the size of the input array. Okay, and as I said, we run this iterations again and again till the time the start pointer has not crossed the end pointer, or we can say in mathematical terms that start pointer is less than equal to end pointer. So again, that same formula, mid pointer is equal to start plus end by 2. And if we have found at this middle pointer the target value, then we return true, that yes, this we have found the target value here. Otherwise, if the middle value is lesser than the target, then we need to move on the right. For moving right, we update the start pointer to mid plus 1. And if the middle value is greater than the target, then we say that we need to move on the left side. For moving on the left side, we say that end pointer needs to be mid minus 1 now. And obviously, if there comes a case that start pointer has crossed the end pointer, or or we can say end pointer is lesser than start pointer, so we can say that yeah, no, we were not able to find this target element in the input array, so we return false. So this is the pseudocode. Now let's. I would I would write the function, binary search function here. You can see I've created that same array which example I showed you in the dry run. That same array I have taken as input, and the target is 12. Okay, we would try to find the same 12 as the target here. Okay, and if we are able to find it, we would print that, yeah, yes, this target is present at index, and this function, binary search function, would return the index where the target is present. So we would print the index. Okay, so let's create the binary search function. As you can see, it has taken two arguments. One is the input array, other is the target value which needs to be found. So let's first define n, which I said is the size of the input array. Okay. Then let's initialize the left pointer, which would be 0, and the right pointer, which would be the index of the last element, which would be n minus 1. Okay. Now let's write the while loop here. And as I said, this while loop would run till left pointer has not crossed the right pointer. Okay. Not crossed means left pointer is on the left or equal to right pointer. And obviously the first thing we do that is we calculate the mid pointer here. And I'm writing this code in the C++, but this code can be easily translated to any other language like Python or Golang or Java, anything. Okay. So mid pointer would be start, oh, left plus and right, left plus right by 2. Okay. And now that if else conditions, we check that if this input mid, the value at the mid value is equal target, then we say that we have found our target, and we return the index at which this target has been found, which is equal to mid. Else if input mid, or basically the mid value, is lesser than the target, then we say that we would have to move right. So for moving right, what we do, we update the left pointer to be mid plus 1. Else if only one case is remaining, but still I would write that else if condition, that target is lesser than the input, basically the middle value. Target is lesser than the middle value. Then we move leftwards, and for moving leftwards, what we do right equals to mid minus 1, and this would continue till we return mid from here. And if we were not able to return anything from here, then this loop would break when the left pointer has crossed the right pointer, which is invalid case. So we would come here after ending the loop, and we can assume that we were not able to find the target element here. So we would return minus one meaning that we were not able to find the target element. So let's try and run this function here. We would try to find this 12 value as our target value in the input array. So as you can see, it prints 12 is present at index 5, which is correct. Okay, and if I modify this target value, let's say 10, which is not present in our input array, and let's try to run this now. So yeah, you can see that 10 is not present. So our binary search algorithm is functioning absolutely correctly. Now, regarding the time complexity of this algorithm, basically we can see from this code here that uh, regarding the time complexity, only what we are doing, basically we are running some iterations only, okay, and in each iteration we are doing some simple calculation like addition, division, and if condition equal to. So basically these are just simple calculation that we are doing again and again for some iterations. So we can say that these calculations are constant operations, O1 operations. So basically, the time complexity of binary search is governed by how many times we are doing these O1 operations. So basically, we just need to find that how many times this while loop would run again and again, and that basically would be the big O time complexity of the binary search algorithm. So let's try to find that. So basically, for finding that, I have written some things here. We as we saw that in that dry run that we were doing on that array, we saw that every time we were calculating the mid element, which was left plus right by two, and then every time during the updation of the left pointer or the right pointer, we were moving towards the left or the right of the middle value. So we can say that every time the search area was getting reduced to half, like if initially the search area was n elements, then in the second iteration the search area would only be n by 2 elements, and then in the third iteration the search area would only be n by 4 elements, and this would happen till we get a search area which is only a single element, right? So basically our while loop would run in the worst case as many times as n gets reduced to 1. Okay, so basically let's suppose n equal to 8 elements initially. So our search area was 8 elements initially, then it would reduce to 4, then half it would reduce to 2 only, and then half only one element would be remaining. So as you can see, our while loop would have run three times. First on the 8 elements, then on the 4 elements, then on the 2 elements, and then on the 1 element. We can basically say it runs around 3 times or 4 times, 3 4 times. Okay. So basically, uh, we what we as I said, we need to calculate in how many times this n gets reduced to 1 on dividing by 2. So that's what I've written here, that when 8 is divided by 2 three times, then it gets reduced to 1. So similarly, if we apply mathematics on the n case, we can say that the x, which is equal to we can say that x is equal to the number of times we need to divide n by 2, so that n equals so that n becomes 1 on that many divisions by 2. So basically, we can say that x is equal to number of iterations in while, or number of iterations of the while loop in the binary search algo. So that's what we need to find for getting the time complexity of binary search. So if so, this would become n equal to 2 raised to x, and if we apply a logarithm on both the sides, so we get x equal to log n. So basically, log n number of times the while loop would run in order to find the target element. And this is basically our time complexity of binary search, which is big O of log n. Now, regarding the space complexity, as you can simply see that in this binary search algo, we haven't used any extra space. Like we haven't created any extra helping array for our operation. We are just creating two, three variables, and these variables do not depend on the size of the array, right? If the input array is 1 million in size, 1 crore in size, or 100 in size, every time our we would require only four variables, this end, left, right, mid, that's it. So our space complexity is constant, so we can say time complexity of binary search is big O of log n, and space complexity of binary search is constant, which is big O of 1. So yeah, that's it about binary search algorithm. Thank you for watching.